Okay, so your exam, if you have not taken the exam, you got to get in there by 6:30 tonight. So, and then you have till 8 to work. So you can take as long as you want once you're in there. Just curious, how many have not taken the exam? Most of you. You're going to go after class. Okay, so today's material, we'll start the next stuff, which is rational functions. Rational functions are not on the exam, but a lot of it is like using all that we did with polynomials. So there's a lot of good review of polynomials in today's class, but the actual new topic is not on the exam. Okay, so does that make sense? All right, so let's get right to it. So if we're turning in homework, right? We got homework? Yeah. Written homework. So let's do that. So if you want to do that problem again in recitation, and then I have another one for you also. So see me after class. Okay, so rational functions. You notice in rational is the word ratio. So that's why we call them rational functions, because it's the ratio of polynomials. So we learn something about polynomial functions. We take one polynomial function, and we take two polynomial functions, we set up a fraction or a ratio. And that new function that we get would then be called a rational function. Okay, so we're going to talk about, we're going to have so in terms of rational functions, these three things we'll still be looking at in order to analyze and sketch graphs of rational functions. We're going to talk about roots, Y-intercept, and behavior, and then there's going to be one more thing that's kind of new to these that we'll work on. But the idea of roots, Y-intercept, and M behavior, it's the same premise. So, for instance, roots. So just as warm-up here, you should all be able to write out a short definition of what a root is. The root of a function is, whether it's a polynomial or any kind of function, the root of a function is, okay, so that x-intercept is not the definition of a root. That's another way to say a root. Okay, so that's the graphing way to say a root. So everyone, so root, 0, or x-intercept could be interchangeable there as what we're defining. Okay. So the root, or the 0, or the x-intercept of a function is, can you write out a phrase that precisely defines what a root is? Everyone give it a shot. You should be able to. So how would we define what a 0 or a root or x-intercept is? Everyone write down what you think. Write out the best definition that you can. Okay, let's see. So Hamid wants to try. What do you think?
It's the number that if we plug it in, we will get 0 for the function.
He said the number that when we plug it in, we'll get 0 for the function. What do you think? Taz likes it. Christian likes it. Anyone? What did somebody else write? So, Patrick. But yours was different. Tell me what you wrote.
I just said that it's the number you would put in, which would result in 0 output.
An input that would result in a 0 output. Yeah, good. Okay. Or you could have said it's x value that gives 0 y value. That's right. So those are all good definitions, right? So we're looking for inputs or x values that give the output or the y values of 0. Okay? So it's the same thing here. So when we look at a rational function, now we just have it in the form of, it's going to be the ratio of two polynomials. So we need that ratio. We need values of x, or inputs, that make that ratio equal to 0. And how will we find those? How will we get? We're looking at this ratio here. What are we going to do to find values of x that are going to make that ratio equal to 0? What makes a ratio equal to 0?
I just add 0 to the numerator.
Add 0 to the numerator?
Yeah. I mean, like, the numerator should be 0, the that value should be 0.
Okay, he wants the numerator to be 0. Was there a hand over here? Oh, no, so you're saying the numerator or the denominator? Either the numerator or the denominator? Just the numerator. What makes a fraction 0? So does the numerator, if the numerator was 0, would the fraction be 0? Yeah, because 0, if you have nothing and you divide it, it doesn't matter how many pieces you divide 0 up into, right? You still have 0. Exactly. So what about the denominator? Should we make the denominator 0? No, that'll make this undefined. You can't take something and divide it up into 0 pieces, right? It's impossible. So if we want the roots of a rational function, we're going to focus on, where are we going to focus? Numerator, and we're just going to find the roots of the numerator. If we get the roots of the numerator, those will be the zeros of the numerator, and it'll make the whole fraction 0. So the roots of n of x are the roots of r. So we're going to focus on the numerator. So that's all we need to, so now we can do it because we know how to get roots of polynomials. We like the factored form, right? If we get the factored form, we just look at each factor and we see what values of x makes each factor 0. So there's nothing new to do there. What about the y-intercept? If we want the y-intercept of a rational function, how are we going to find it? Somebody new? How about... I'm just blanking on names here. Malin, how do we find the y-intercept of a function? Where the x value is 0. So what are you going to do? So we got this function. What are you going to do? Yeah, that's it. How are you going to find the y-intercept? Omar.
Just plug in 0 into x and find the y-intercept.
Yeah, it's going to be r of 0. So the y-intercept is going to be r of 0. And how do we do that? It's going to be, you're going to plug 0 into the top, and plug 0 into the bottom. And you're going to solve that. And that'll give you the y-intercept. Okay? End behavior we're going to do later. Okay, so we're going to do end behavior later. But so roots, where are you going to focus? You're going to focus on the numerator. Because whatever makes the numerator 0 is going to make the whole fraction 0. So the roots of the numerator are the roots of r. Y-intercept, same as always. We want to know the y value when x is 0. So we plug in x equals 0. All right, so there's this other aspect to this number 4. We're going to skip now to number 4. And so if you look on page 222, I want you to, let's read the setup together. Top of page 222, number 2. Okay, page 222, top of the page, number 2. It says 5 gallons of liquid flavoring is poured into a large vat. Water will be added to the vat and mixed with the flavoring to produce a drink that will be bottled and sold. Okay, so it's like syrup, right? It's like, I got the concentrated syrup, we're going to mix it with water to make this drink. Okay? And so they say, suppose water is added until the total mixture is 7. What is the ratio of flavoring to water? So before we start answering these questions, we should notice that there are really 4 different quantities flying around here that we have to keep track of. First quantity is the amount of syrup or flavoring. And what do we notice about the amount of syrup or flavoring in the situation? Always 5. It doesn't change. Okay. Next is the amount of water. Okay, so the number of gallons of water. And then the next one is the number of gallons of the total mixture. And then the final quantity is the ratio of flavoring to water. So as you're answering these questions, you're keeping track of all 4 quantities and making sure you have the right things in the right places. Okay? So you're going to work on A through C. I'm going to take attendance. Work on A through C. Go slow. Make sure you're reading correctly and answering, doing what they're asking for, okay? So read carefully and do A through C. Any questions? Yeah, question?
Are they continuing to add the flavoring fluid or just pouring in more and more water?
No, suppose water is added
Right.
until the total is 7. Yeah, it's going to stay 5. The flavoring stays at 5. That's right. So A and B are kind of warm up for C. C is the important thing. So the A and B are kind of warm up for that. You want to show me what you've got so far? Check it. Or Megan? So this is ratio 5 was a fraction. Get an actual 1 number. Okay, so a fraction gives you 1. So what? Lots of great answers here. So when it says ratio, actually set up a fraction so that you're actually getting a single value in the end, right? So by ratio, make a quotient, make a fraction. Okay, Morgan, how did part A go? Tell me, what was your process or your thinking on that one? With the rate. 5, okay. Okay. 2. And so then what's the ratio? So she said she took 5 gallons of flavoring divided by the amount of water, which would be the total minus the flavoring. And that would be 5 over 2. Agree with that? Oh, agree with that? So you get this number 2.5. What would the meaning, in this context, what is the meaning of 2.5? How could you describe the meaning of that number? What does the 2.5 mean? Austin, any idea?
There's 2.5 gallons of flavoring for every 1 gallon of water.
He said there's 2.5 gallons of flavoring for every 1 gallon of water. Do you agree with that? Or what if it was just any amount of water? So you have any amount of water, what could you say about the amount of flavoring?
There's 2.5, but it down for 1 gallon of water.
But if there's any amount of water, so if I just had, I
2.5
could,
times that.
Audie,
Yeah, that's what he's saying.
yeah, 2.5 times as much, right? So if you have any amount of water, your amount of flavoring is going to be 2.5 times as much as that. Make sense? Okay, Walter, how about part B? Talk me through it.
I did 5 over 13.
Where did the 13 come from?
I subtracted 5 from
So the 5 is the amount of syrup, and the bottom is water. So we got 5 to 13, and we get, is it 0.38? Anyone? About 0.38? So what does the number 0.38 mean? Taz, so could you explain that number 0.38?
For every gallon of water, there's 0.38 gallons of syrup.
For every gallon of water, there's 0.38 gallons of syrup. Okay? Or for any amount of water, how much syrup do we have? Yeah, so a little bit more than a third of the amount of water that we have is going to be syrup. Okay, so we want then the function. So now we want the, and what's the input of our function? What is it? Total volume of liquid. Or drink in gallons. And what's the output going to mean here? The output is, what do they say? It's the ratio. So Diana, did you get it? So 5, the number of gallons of flavoring over, and what does x minus 5 represent? Just the x minus 5, what would that mean? And what would that give you then? Yeah, if you took the total volume and you amount of water, right? So that denominator is the gallons of water. Okay, so this is our ratio. So this function takes the total amount, or the final amount of the mixture, and gives us, spits out how much, what that ratio that we talked about earlier, that ratio of flavoring to water. Any questions on A through C? Okay, so what we see here is this is a rational function. So 5, we wouldn't have thought of that as a polynomial in the past, but it is, right? Because it's the sum of many terms with a base of x, and so it follows the form. Even though there are no terms that have x in them, this is really like 5x to the 0, right? Okay, so that can be thought of as a polynomial, although it is just a constant. Okay, so this is a rational function because it's like one polynomial divided by another. Okay, so we want to kind of investigate this effect of this denominator. All right, so we have this denominator here, x minus 5. So what we want to do is look at this idea. What does it mean to say as, so x arrow 5 plus, x arrow 5 plus, this is part D. And so what this means is x approaches 5 from the right. That plus means from the right. So x approaches 5 from the right. That's what this x arrow 5 plus means. So really it's kind of represented, or we think of it as like something like a sequence of values that are greater than 5. So if we think of the number line, say here's 0, 1, 2, 3, 4, 5. So from the right means values greater than 5 over here. And so it's a sequence of numbers greater than 5 that are decreasing and getting closer and closer to 5. That's what this means. X approaches 5 from the right. So, like I said, a sequence of numbers greater than 5 that are decreasing and getting closer and closer to 5. So let's make up such a sequence here. So where could we start? So there's no one right answer. There are many wrong answers, but there's no one right answer. Where might we start if we wanted to kind of represent this x approaching 5 from the right? What x value might we start at?
7.
7. That's reasonable. And Jaden, where do we go from there? What would the next x value be? We want to approach 5 from the right.
6.9999.
6.9. Okay, so where are we going in the end?
Left.
To what?
Negative.
But to where? Where are we approaching?
5.
5. So to go from 7 to 6.99 doesn't make much progress, right? Because what's our end goal? To get to 5. So let's get there a little quicker. 6. Then what?
5.5.
5.5. Someone take over from there. Nadine. 5.25. Then what?
5.125.
How about 5.1? Okay, now I want to get closer. I want to keep going. Taz. All right, if I put, let me do one in between here. So here's 5.01, and then how many zeros did you want? This is the idea. So there are many ways to create this list. This is the idea of x approaching 5 from the right. Numbers greater than 5, decreasing to get very close to 5. Okay, so what we want to do is we want to investigate then our function, our function, the ratio function, which was our f of x. As x approaches 5 from the right, what does this ratio do, or what do the outputs of the function do? Okay, so rather than everybody calculating all of them, everyone just pick 2 or 3. Don't everyone start, just pick anywhere. Pick any 2 or 3 that you want and calculate the corresponding ratio for the input. And then we're going to look at the sequence of outputs and see what the sequence of output does as x, or the total amount of mixture, approaches 5 from the right. Okay, go. So pick 2 or 3 and calculate the output of our function. I'll write it again up here. Where should I write it? I think that's the next slide. So this is what we're asking. What happens to r as x, we're doing actually e now. What happens to r as x approaches 5 from the right? So how do we get r? 5 over x minus 5. So pick 2 or 3, calculate the output. Pick any 2 or 3 from the list. Okay, so who did 5.5? So when the total mixture is 5.5, what was the ratio? Some people are hearing 10. Is that right? All right, how about 5.25? Nice and loud. 20. Okay, how about 5.1? All right, let's stop right there. So 50. So, or let's do one more. What's 5.01? Okay, so what I want you to do is, with your partner, I want you to first interpret the meaning of the number 500. What does that number mean? And why does it make sense if the input is 5.01? Okay, what does the number 500 mean? Why does it make sense when the input is 5.01? Have a conversation. Go. So I'm asking you what this means. I'm not asking you to just say it's the ratio. Okay, what does that ratio mean? What is that number telling you about stuff involved? Okay. Yeah, but why? What's going on? Talk to me about the meanings of these numbers. The meanings of these numbers. Okay, how about the 500? What does that number signify or represent? Brian. He said there's 500 times as much flavoring as there is water. Agree with that? And why does that make sense when our input is 5.01? Christian, go ahead.
5 divided by 0.01 is 500.
No, but so I'm asking about why does it make sense? What's the meaning of 5.01, and why does it make sense then that the ratio of that there'll be 500 times as much flavoring as water? Fuda. Okay. Good. Good. So she said this means that there's 5 gallons of flavoring and just like a drop of water, right? 0.01, or maybe like, it's a fraction of an ounce of water. And so therefore there's a lot more flavoring than there is water, and so that was that ratio so high. So what's happening as the total amount of mixture goes down and we keep the amount of flavoring the same? What happens to that ratio of flavoring to water? It increases. How much does it increase? Anyone get this one? What's this? 50,000. And we could keep getting as close to 5 as we want. And what's going to happen to that ratio, or how many more times flavoring there is than water? Yeah, so we can keep putting a smaller and smaller fraction of water in there, and as we do that, then how many times greater the amount of flavoring is to water is just going to skyrocket, right? It's just going to skyrocket. Okay, so let's see what happens with the graph then. So here we are coming along here. Here's say 7, 6, and then our 5.5, and so we're looking at numbers getting very, very close to 5. So this on the graph, moving this way towards 5 is our x approaches 5 from the right. That's our sequence of numbers, like that. And so we got our data values here. We got our data points. We started with like 2.5. And then we had 10. And then we had 20. And then we get close to 5, and the amount of flavoring compared to the amount of water just shoots up, skyrockets. Like this. What about x equals 5? What happens to the ratio of flavoring to water if x equals 5? There's no water. So what about the ratio? Yeah, it's undefined. It's so huge that you can't put a number on it, right? It's undefined. And so what happens is we can't plug 5 into this function. And as we get closer and closer to 5, we see this value of the ratio just shooting up to as high as we want, as long as we get as close to 5, close enough to 5, the small enough amount of water, we can get any ratio to infinity. So we have this imaginary line here at 5, which is called a vertical asymptote. The rational function is undefined at that value of the vertical asymptote, because if we put 5 in that function, it would be like trying to divide by 0. There's only 2 people that can divide by 0. Yeah, don't you remember from last semester? Yeah, so it'd be good if I knew. I can't think of his name. What's the guy from Texas Hawker Ranger?
Chuck Norris.
Chuck Norris can divide by 0, right? Chuck Norris can divide by 0. Okay? And then one other person. My daughter, Emma. She can divide by 0. This is her. She did it more than once. Okay. That was last fall. I don't know how many times she's done it since then. But that was in the fall. Okay. Yeah.
Can I say one more time the meaning of R?
Meaning of R, the output of the function, it's how many times more flavoring we have than water. It's the ratio of flavoring to water. So like for instance, when you have 6 gallons total, that means 1 gallon of water, 5 gallons of flavoring. So you have 5 times as much flavoring as water. Does that make sense? So when you have 5.1 total gallons, 5 is flavoring, 0.1 is water. So you have 50 times as much flavoring as water. So as that input value of total amount gets closer and closer to 5, the water is so small that that ratio then goes really, really high, because there's so much flavoring relative to the very little amount of water. So this is what that graph looks like. Okay, so this is the fourth thing that we have with rational functions is what's called vertical asymptotes. And where do those occur? So now we look back at our function. It was 5 over x minus 5. So what are we looking at to find vertical asymptotes? Denominator, right? So as we get close to that root, that's the root of the denominator is 5. As we get close to that 0 in the denominator, we get this behavior where the ratio or the fraction gets really, really large as you get really close to that root. And then at that root of that denominator, the function doesn't exist. You can't get a value. Okay? So if we were to, what only makes sense in this situation is values greater than 5. Right? You can't, if you have 5 gallons of flavoring, you can't have less than 5 total, right? But if we remove this situation, we could look at this function and we could consider values of x less than 5. We can do something else instead of that. All right, so the next example will take care of that. But here's our graph for total number of gallons of final mixture and ratio of flavoring to water. And so we see this behavior as you get close to that root in the denominator, you get this really high positive value, in this case, for the output of the function. So now look at number 3 there. There's a table there for any questions about that? Anybody have a question? So look at number 3. F of x equals 1 over x minus 8. Where are we going to have a vertical asymptote, first of all? X equals 8. Okay, look at that list of numbers. How would we represent that, what's going on there with that list of numbers? So if you go 7, 7.5, 7.9, 7.99, we would be saying x is approaching what value? 8 from the left, so that you put a minus. That's what that means. X approaches 8 from the left. Okay, and so when we do that, if we plug those values into that function 1 over x minus 8, here's what we get. We get -1, -2, -10, -100, -1,000. So we've seen the same kind of effect. As we get close to that vertical asymptote, or we get very, very close to 8, that root in the denominator, we're getting these numbers that get very, in this case, very large negative. So those are the two possibilities that can happen near a vertical asymptote. As you move towards a 0 in the denominator, your function can either go up very sharply to positive infinity or down to negative infinity. So in this case, if we were to sketch what we're looking at there, just quickly, let's sketch it. So there's 8. So now we're saying x gets closer to 8 from the left. And what's happening as we do that? The closer we get to 8, the larger of a negative number we get. Okay, so this is the behavior near an asymptote. It either gets very, very large negative or very, very large positive. On both sides, okay? On both sides of the asymptote. Okay, so now we're going to put it all together. Oh, we still haven't talked about M behavior, but we got these 3 things so far. So go over to page 225, number 6. And for just A through C, I want you to find what we've talked about so far. For each of those functions, find the roots, find the Y-intercept, and find the locations of the vertical asymptotes. So my experience, in the first class, my experience was that as we tried to do this, we had our wires crossed everywhere. So you've got to really be confident. Where do we focus? What do we look at to find the roots, values of x, that make the function 0? How do we find the y-intercept? Where do we look and how do we find the locations of vertical asymptotes? So just A through C, and those 3, I want you to find those 3 things. So I'll list them here. Roots, the y-intercept, and the, what do we say, vertical asymptotes. All 3 for A through C. Very good.
Plug that to and distribute it, so it's 2x. We have just a number all the way to the right. If there's no x. Just for that.
Okay, Joe. What are the roots for part A? The roots. What's that? Infinity? But I want the roots of f. I want to know about the roots of f. What is a root? What does it mean? None? Why none? He's saying fx can't be 0. Agree with that? So what do we look for roots? Where do we focus our attention if we want to look for the roots? Numerator. So we're asking, what are we asking? Values of x that do what? That make the numerator 0. What values of x will make 8 into 0? Doesn't exist. 8 is always 8. There's no x value that'll change an 8 into a 0. He's right. There's none. There's no roots to this function. It never crosses that. There's no x-intercepts. Okay? The y-intercept is f of 0. So 8 over 0 plus 1, or 8. And the vertical asymptotes, x equals -1. Questions on part A? Is it okay? Okay, how about the roots of g? Jared, right here, Jared R. 0. You're looking at what? Yeah, so you're looking at the numerator. We want to know what value of x makes that numerator 0. Well, x equals 0, we'll do it. What about the y-intercept? Shola. What's that? For the y-intercept for g? Not sure? So tell me about the y-intercept. What's true at the y-intercept? Yeah, g of 0. G of 0 will give the y-intercept. So what do you get? What's g of 0? 0. Yeah, if you've got a root at 0, that has to be the y-intercept too, the origin. Then origin is your y-intercept. Okay, vertical asymptotes. Justin. And how'd you get that?
Well, I solved for x at the bottom.
Yeah. If it were equal to? Yeah, so we want a 0 in the denominator. So you could factor that if you want the factored form. 2 times x plus 4. X minus 4, sorry. Or just solve this. And so you get x equals, like you said, x equals 4. All right, questions about A and B? All right, so I've got C on a different page here. We'll do C, and we're going to, where's it? Turn it off there. Let's turn it off. Okay, so here's C. So the roots. What are the roots of C? Somebody new. Jaden. How'd you get it? So you took. So did you start by adding 24 and then dividing by 6 and you got x squared? Okay, so that's valid. You could add 24, divide by 6, get your x's. What do we like for finding roots? What form do we like for finding roots? Yeah, so let's factor it. What you did is perfectly fine. So how does x squared minus 4 factor? X plus 2, x minus 2. So we could rewrite our numerator this way in the factored form for that polynomial. 6 times x plus 2, x minus 2. Clearly the roots are 2 and negative 2. Okay, y-intercept. Audie.
You said x is 0.
Okay.
And so it becomes 6 times 2, negative 2, 2, negative 3, 1.
What's the numerator when x is 0?
6 times 2 times negative 2.
When x is 0?
Yeah.
You're trying to put the roots in. We want x to be 0. Right? The y-intercept is when x is 0.
Right, so if you put 0 in for the factored form.
Oh, I'm sorry. Okay. I see. Okay.
So it's 6 times 2 times negative.
I got it. Sorry. All right. So you get negative 24
Yep.
divided by
Negative 6.
4. All right. So I'm going to start graphing these. So negative 2 and 2 are our roots. 4 was our y-intercept. Okay? Vertical asymptotes. Let's see. Christina. Did you get the vertical asymptotes? 3 and negative 1. X equals 3. X equals negative 1. All right, so we know those are imaginary. They're not part of the graph, but we sketch them to help us make the graph. So there are these imaginary vertical lines. where the function is undefined, and we know that as x gets close to those, one of two things can happen. Either the graph is going to get very large positive or very large negative. Okay? All right, so the last piece of the puzzle here is end behavior. Okay, so end behavior. So how did we find end behavior for a polynomial? Leading term, Omar says, right? So this function doesn't have a leading term. Really, there's two polynomials, so it has two leading terms. So we'll go with that. And so as x gets very large, what will the numerator be like? So as x gets very, very large, the numerator will be like, what's our leading term, Corey, of the numerator? 6x squared. And what's our leading term of the denominator, Corey? 2x squared. So when x gets very, very large, either positive or negative, the numerator is going to essentially be 6x squared, and the denominator is essentially going to be 2x squared. So that whole ratio is going to be essentially what? What do we get? 3. So 3 is not the leading term. There is no leading term of this function, but it kind of is in effect. In effect, it's like the leading term of that function. So we call it the effective leading term. So 3 is the effective leading term. It's the ratio of the leading terms of the two polynomials that we use to build the rational function. So what does this mean? It means that as x gets really, really big, positive, as we go way out to the right, what will this function be like? What will the y value do? It'll be really close to 3. And as x gets really, really large negative, we go way out to the left, what will this function be like? 3. It'll get close to 3. So now we have this kind of new situation. Remember, with polynomials, it either went up to positive infinity or down to negative infinity at the ends. Well, now it's possible that we get it just kind of levels out at a certain value. That's what's happening here. The y value is going to level out for large values of x. It's going to level out at 3, and it's going to level out at 3 for large negative values of x, because that's what our leading term is, right? 3. So we have, way out here at the ends, we have, it's going to get closer and closer to 3. Oops, that's too high. So that's 4. Try that again. So 3 is down here. So 3. So now we can put it all together and sketch this graph. Okay? So I'll sketch it in black. So it's going to get really, really close to 3 out the ends. And we know that as we get close to this vertical asymptote from the right, it's going to do one of two things. Really large positive or really large negative. But we know which one it has to be. Which one does it have to be and why? He says positive. Why does it have to be positive? What happens if it's negative? No, I'm talking about, what's that? You'd have a root there. So see if this was going out to, if it was leveling off at 3, but going down here to negative infinity, as you get close to 3 from the right, you'd have a root in here. We don't have it. Therefore, it has to do this. Okay? And so we know it's going to go through that root and that. And then again, multiplicities still hold, are the way the multiplicities work. So this numerator was 6, x minus 2, x plus 2. What are the multiplicities on those factors? 1, meaning that at those roots it's going to go straight through like a line. So we have that right here, going straight through like a line. Therefore, as we get close to 3 from the left, up to positive or down to negative? Because no root here. In order for it to go up to positive, there'd have to be a root here. It'd have to go through and come back, and have to be a root. Same thing here. There's no root here. So when it goes through that y-intercept, then it has to go up to positive infinity. Okay? Out at the end, it's going to be like 3. Since there's no root here, it's going to come through. Multiplicity at negative 2 is 1, so it goes through. Down to negative, up to positive. There's no root here. It's got to go down to negative. Here's this graph. All right, turn it on. I'll do purple. Okay, so got it. So we got the roots, negative 2 and 2, vertical asymptotes, 3 and negative 1, y-intercept 4, end behavior 3. So how can we confirm the end behavior? How should I transform this graph? What should I look at to see that the end behavior is indeed 3? What should I do? What's that? Zoom out on what? Specifically. Yeah, if I zoom out on the x-axis, then I'll be showing really, really large values of x. What do you expect the graph to look like? Should look like? Straight line at 3. So let's see that. Here we go. So as I zoom out, so we're disregarding the middle behavior now and just looking at the end behavior by looking at large values of x. I have not changed the function that I'm graphing. I'm still graphing the exact same function here, that rational function. But I'm just looking at huge values of x to the right and to the left. And what do we get? We get 3. That was what we predicted for the end behavior. The effective leading term was 3. If I zoom back in, then we'll see all the middle behavior once we get to these small integers. And that's pretty cool. Okay, any questions on this process of sketching rational function?
How do you connect the y-intercept
Uh-huh.
and the x-intercept? Why is it curved like that?
Why is it curved like that? So, since there's no other roots in between, so there's no other roots here in between, it has to be heading down from this one to there. So do you mean like why is this concave up and this is concave down? Is that what you mean? Is it okay? All right. All right, other questions? Okay, so here's practice for you guys. Ready? So no graphing calculator. Whenever, okay, so, right, yeah. So no graphing calculator. No, let's go right to this one. Let's do this one instead. Go. So no graphing calculator. Build these 4 things that we're talking about, and then try to piece it together. Try to sketch the graph by putting those 4 things together, like we did. effective leading term, right? So how do we find the effective leading term?
Wouldn't you first expand the brackets below?
Let's expand. So as x gets really, really big, what's going to govern on the top? What's going to be like the top? Yeah, but it's precisely what will it be like? That's what's really, really big.
It'll be like 7, like number plus 7.
No. So when x gets really, really large, what's going to happen to that? It's going to be like what? If you put a billion into that, what will it be? What will the result be like? This is polynomial stuff, right? So what do you look at? If you're just looking at that numerator as a polynomial, what do you look at to determine the behavior? Okay. What about the denominator? X cubed.
So it's x squared
Right. Which is what?
2x minus 1.
That's, in effect, the leading term of this rational function. What you said. Maybe. So. Oh no, you're missing an asymptote. There's 3 asymptotes.
There's 3? Yeah.
Oh, yeah.
Okay, let's see how you did or what progress you made. Brooke, how about roots? Did you get any roots? Okay, that's a good start. And how'd that work out? But you get 2x squared equals, no, not 7. Negative 7. And so now we got x squared equals, and what about that? Now we just got to think about that. Yeah, so we could take square root. Right, so conclusion? No roots. No real roots, right? So you can get imaginary roots, but we're graphing on the real plane here. So no roots. Should have gotten that. Which means what for the graph?
So won't cross the
It's never going to touch or cross the x-axis. We're going to no x-intercepts, okay? Y-intercept. Yeah, Justin. 7/4. It'd be 7 over -1 times -4, which is 7/4. And I believe that's 1 3/4. Is that right? Right there. Okay, so 1 3/4. Vertical asymptotes. Austin.
positive 1, negative 1, 4.
You got 1, -1, and 4. Okay, not part of the graph, but we sketched them. Good enough. Know that the function does not exist at those x values. Okay? End behavior, effective leading term. Alex, did you get it?
No.
What would you do? If we want to find the effective leading term, remember what we do?
So you find the numerator,
Uh-huh.
leading term, which is 2x squared.
Good.
Then you put it over 1 for the denominator, 2x cubed.
Good.
And after that, I did it.
Simplify. What is that? simplified version of that. 2 over x. Okay, so as x gets really large positive or goes way out to the right, what will y do? So think 2 over an exceedingly large number. He wants to approach 0. Is it closer to 0? Yep, that's what that does, right? Because that will just be smaller and smaller and smaller as x approaches negative infinity. What about now? So, yeah, so right, it'll still approach 0, but it'll be negative, getting closer from underneath, right? So this will approach 0, but there'll all be positive numbers decreasing to 0. And this will approach 0, but it'll be negative numbers increasing to 0. So we can kind of, let's draw that right now. So that's our end behavior, approaching 0 at both ends. From the positive side when x is positive, and from the negative side when x is negative. Okay, so now let's put it all together. So we know we're never going to touch or cross the x-axis. All right, so as we get closer to this vertical asymptote, up to positive, down to negative.
Positive.
Because?
No root.
No roots. If it went down to negative, there have to be a root somewhere in there, and there's not. It's got to do that. Question?
No, just
Okay.
aspect is left to right.
All right, so how do we know what's happening in between here?
I put numbers in,
Okay,
like 2 and 3,
good.
and I got around -3, -2. So I know that there was
For both of them?
Yeah, around both of them. Not exactly, but
All right, so here, this is great. It's because we kind of don't know. Like, we know it doesn't work crosses, but is it always positive, always negative? So he just plugged in a few values. Plug in 2 and 3, and he got negative values around -2, -3 for both. So that would indicate that as we get closer to 4 from the right, it's got to go down to negative. Similarly, as we approach 1 from the, 4 from the left, 1 from the right, it's also got to go down to negative. It's always going to be negative through here. Boo, right? So by plugging in a couple values, we get negative values. If it never crosses, then it's always got to be negative between those two asymptotes. All right. What about here? Same thing for here.
no more roots.
No more roots. If it goes through that, then it's got to go up to positive. Up to positive. Same thing here. Approaching 0. As we get close to this asymptote, got to go down to negative because didn't quite make it. Imagine that getting closer. Something like this. Let's turn it on. I'll make it red for contrast. Okay, any questions? All right, so your homework for Tuesday will be on this rational function stuff. Check Blackboard. Of course, don't forget the exam. Got to be in there by 6:30. Many of you have recitation now as well. If you've got a question, catch me on the way out.